asked you to look at the code of harmonic oscillator. Let's do that first. So it's exactly the same code. The only difference is that we have this V, the potential is defined, okay? And how do we define it? We need to define omega. I've defined it as 2 pi radian per femtosecond, okay, let's say, just any number. K is mass of electron times omega squared. Do you remember that from harmonic oscillator? What else do we need? Okay, it's not exactly the harmonic oscillator. It's a bit different because I still put the boundaries to 0. While in reality, harmonic oscillator has no bounds. It can, in principle, go on forever, right? There are numerical techniques to take into account that kind of situations, which involves discretizing differently. Like you discretize the middle part more with more grids, and as you go exponentially far away, you put less and less points, okay? That's another story, but we are using same grids. We just put it at 0 far away, far enough away, okay? Or we take the stiffness high enough so that the wave function is confined more or less. You will see it when I run it. So the only thing that changes is that now you have a potential that looks like this. It's kx minus L over 2 squared over 2. Why it's x minus L over 2? Because our spring is at the middle. So the far away you go from the middle, the more the spring wants to bring you back, okay? Does it make sense? All right. The rest of the code is the same code. So let's run it. So how do we start? Let's look at how do we start. By the way, Hamiltonian is kinetic energy plus potential energy. And eigenvectors and eigenvalues are calculated with respect to Hamiltonian. And I start from, let's start from eigenvector 1 and plus eigenvector 2, okay? Let's see. Do you remember how it was behaving when it was particle in a box? It was going back and forth. Okay. Same story here. Okay. Goes back and forth. I just took the stiffness high enough so that it's confined over in this region. When I move with mouse, it stops for me, like wonders what I'm going to do, so that's why it stops. You see? By the way, I'm also writing down the energies here. Look, these numbers are the eigenvalues. Let's look at here. Let's look where I'm plotting it. So diagonal of the eigenvalues from 1 to 10, and that gives you first 10 eigenvalues, divided by h bar omega. So if you divide by h bar omega, what do you expect to get for harmonic oscillator? H bar, so you divide this energy by h bar omega. What do you expect? M plus 1/2, right? So you expect to get, start with a half, then 1/2, then 2/2, 3/2, 4/2, 5/2. Okay? We do get those energies. Very nice. Why it is not exactly that, right? So that's numerical precision. So if I don't discretize by 200 but by 1000, let's say, then it takes longer time and it fixes the first few, but then the rest is again problematic. Okay? It's numerical precision. All right. Sure.
Can you make it periodic?
Periodic?
The potential periodic. because it only requires only two terms changes.
Why do you want to make it periodic?
To just like see how it looks like.
Let me draw the potential right now. So this is how the potential looks like right now, and you want to make the system periodic, the whole system periodic. Okay.
I just want to change boundary conditions since you said it's zero now.
Yeah. Okay. So then, how would you do that? Well, we need to change the code a little bit too much, I guess. I need to put, I think, this. Oops. Let's come to that when we come to block states. Okay, I will do it anyways. But otherwise, it's the same story. It's the same code. If you, for example, run it and let's say measure energy, it will collapse into one of those eigenstates and give one of those eigenvalues. Okay, restore it, measure again. Now it collapsed into the second one. Okay. Do you have any questions related to this? Or is it clear? Would you like to see what happens when we soften, for example, the spring? So then the wave function is more spread out and it's oscillating slower, right? All right, very good. If I harden the spring, it's more localized and goes back and forth faster. All right. If you have no other questions related to harmonic oscillator, I can move on.
Harmonic oscillator is just like here, yes.
Very good point. I actually have that in my notes. Why do we care so much about harmonic oscillators? Because they are actually everywhere. So, for example, if I have, let's say, two carbon atoms, right? If I plot so this is the distance. If I plot the potential, so there's a repulsive part and then there's an attractive part of the potential, right? So if we focus on this part only and make a plot of that part only, where the system lives, the system is usually there, right? It just jiggles around there. It doesn't go around here. So if you look at this particular part, it looks very similar to a harmonic potential because so second derivative is non-zero. First derivative is 0 because that's where the force is 0, right? And the second derivative is positive. So that's where you get your kx squared over 2, right? It could have some third order, fourth order parts, which gives this shape to the potential, right? It's not like if you continue, it actually does have some imperfection. And that imperfection actually accounts for certain effects. Like, for example, the deviation from harmonic potential actually accounts for thermal expansion, right? Why? Because as you, let's say the bond, right now it jiggles around this point, right? But if it jiggles too much, you can see that the average of the jiggling actually shifts to the right, Do you see it? Because the potential is a bit more towards the right than towards the left. That's why as you heat something, it expands. All right? By the way, harmonic oscillator have also solved one other 20th century crisis already, since we know it now. It solved the heat capacity problem now, because we can think of those diatomic molecules as being balls just connected with springs and vibrating. So it's a harmonic oscillator, and depending on its omega, it can take in only h bar omega, right, energies, and it will actually start getting excited only when kBt is close to h bar omega. All right? Only then it will start accepting the thermal energy that you are giving to the system, right? Before that, we call those modes are frozen. Okay, those modes are frozen. And then you unfreeze them by giving enough energy. So if you remember, we had this plot that went on like this: 3½ 5½ 7½. So our harmonic oscillator theory accounts for this temperature being close to h bar omega over kb. Okay? We didn't really uncover this part. So that part tells you that the rotational motion is also frozen until some point. Let's come back to that, or let's never come back to that. Just figure it out on your own if you are so curious about it. All right. So far, so good. Let's remember how many systems we have solved so far. Box and harmonic oscillator. Is there anything else that we have solved? Do you remember? No, right? So let's talk about the free particle. So what is similar between this box and harmonic oscillator? That they are both bounded systems. Okay, there is no escape for the particle from the potential, because one of them has infinite potential, right, localizing an electron or a particle between 0 and A. The other one goes to infinity as you increase the x, so there is no escape again, right? But what about the free particle? For the free particle, it's actually very similar to the box potential. Box potential was also Vx equals to 0, right? But it went to infinity at some point. Now it doesn't go to infinity at any point, just Vx is 0. That's it. Okay? What does it mean? You simply have a potential that is at 0 everywhere. It goes minus infinity to plus infinity. You have some potential that is 0. So let's say this is the 0 potential, Vx equals to 0. And let's say you have a particle at a certain energy. And this is with respect to energy. This is energy. The blue line is your potential. And this is where your energy is, let's say. So let's see how this one behaves. Again, one particle.
There's no other particle.
No other particle in the universe. One particle, 0 potential. Very good. Then Schrödinger equation, time-independent Schrödinger equation, is h bar squared or 2m d squared phi over dx squared And that's Hamiltonian, right? You have Vx is 0. It should be E phi. Do you agree with this? Any objection? Tell me. No, in the harmonic oscillator we needed Vx as well. Do you remember? We had sort of. Yes, exactly. No, sort of. Let me gather my thoughts. Exactly. Yes, exactly. Exactly. The only difference is that our wave function can be complex number as well. In the harmonic oscillator, okay, let's do it. Okay, let me rewrite it like this. Okay. So I'm going to call this one something. I'm going to call this one k squared. So k is defined as 2me over h bar squared. Okay. Then the equation becomes minus k squared phi. Okay. You are right, just like harmonic oscillator. But not in time, but in space, right? So then I have, for every k, depending on what k is, I can have some coefficient ak e to the plus ikx plus some coefficient bk times e to the minus ikx. Are you surprised by this? Not at all, right? You needed e to the ik, because this one basically gives you lambda. So you propose a solution in the form e to the lambda x, lambda equals plus minus ik, and that's it. Very good. So what does this mean? What does this mean? First of all, can k be anything? Can E be anything? Can energy be anything? Is there something, if you remember, in the case of the particle in a box or harmonic oscillator, E just couldn't be anything, right? The only thing E can't be is, I guess, 0. E can't be 0 in this case, but if you look at the equations, E can be anything. Do you have any objection? Why? What is the difference? Why in particle in a box? Do you remember where the discretization was coming from? Let's remind ourselves where the discretization came from. Especially in the particle in a box, it's easier to see, I guess. So, discretization in particle in a box came from here, right? So the boundary condition that was telling us that phi had to go to 0 at the boundary. So the discretization actually comes from boundedness. Okay? If you are not a bound system, then you are not discretized. So if you have two carbon atoms that are attracting each other and they have nowhere to go, then they are a bounded system, and the bounded system creates discrete energy levels. Okay? The more bounded, the more discrete. Do you remember quantum confinement? So then we can say that, we can conclude that confinement leads to discrete energies. Right? The more confinement, the more discrete, the more pronounced is the discreteness. Okay. Now, if you have no confinement, just like in a particle, in free particle, it's free for a reason. It has no bounds on it. No confinement, continuous energies. Right? So, what is the energy? The energy is h bar squared k squared over 2m. Do you agree with that? Because we have defined k to be 2me over h bar squared. Hence, if you go backwards, energy is h bar squared k squared over 2m. So far, do you have any question? Any question at all? This, you can compare this to E equals to P squared over 2M. What does it tell you? Do you see that it's P equals to H bar K? Do you see it? So this is actually de Broglie's principle. Principle, proposal, postulate, whatever. Now it's supported by the equations. Why? Because look, e to the ikx, which is the wave function of this. Now, for de Broglie, we didn't know what he meant by wave nature. Now we have just a little bit more knowledge about the wavy nature of this. But nevertheless, e to the ikx basically corresponds to a wave, right? That has so this is the sine part, right? And there is also a cosine part. Okay, I might have drawn it. So it should be always out of sync. Probably. Yes, it is the one going to the did you say left? Did it? Yes, it should. Well, we will come to that. Just give me some time. No. E to the ikx goes...
It depends on whether you are an electrical engineer or a physicist.
Okay. A physicist, it goes to the right. We will see. We have the code, we can check it. Or we have our brains, we can check it. Don't worry. So, no, it is the one that goes to the right. Okay? Because momentum is h bar k, and k, when k is plus, momentum is plus, it goes to the right. Okay? Why it is de Broglie's principle? Because if you remember from first lectures, those first lectures were really important. I hope you can see that now. Do you remember what this was? The wavelength? 2 pi over k, right? Or, more famously, k is 2 pi over lambda. Right? Since p is equal to h bar k, it's basically h over 2 pi times 2 pi over lambda. So there you go. P is h over lambda. That's what de Broglie was postulating. Do you see it? Now actually you can go back. I don't know if you remember. I was tempted to try solving particle in a box with de Broglie's principle. So we will do it. We will go backwards at some point and discuss quantum physics one more time and see that it is actually a nice theory. It's just not as nice as Schrödinger's equation. All right. Okay. So let's say I start with phi x of 0 equals e to the I kx. Let's say. What is phi x of t? How would you find it? Do you remember how to find this? Anyone at all? Huh? So this is basically your eigenfunction anyways, right? So you can just simply write phi xt equals the starting eigenfunction times e to the minus e what? K? K, okay, ek times t. By ek we mean the corresponding energy, right? So ek is h bar squared k squared over 2m. Did you follow this? So what is your psi x of t? It's a plane wave, right? E to the I k x minus h bar squared k. That one h bar goes away, right? So this is how your wave will move. Do you have any questions at this point? No questions? What is the speed of this wave? Okay, before we go to the speed, let me ask you something. Can you please normalize this? Okay, let me put an A in front of it. Find A. Can you find A? It's not 1. Anyone? How do you find A? In general, you have the homework right now, right? Normalization. So you have to do this, minus infinity to plus infinity, right? A squared e to the ix with a minus e to the plus ix, ikx. Did you follow this? Equals to 1. So a squared dx equals to 1. A squared times infinity equals to 1. Actually, there are 2 infinities here. A is 0. So the particle doesn't exist. We can go back home. We have a normalization problem with the free particle. Okay? How do we deal with that? How do we deal with that? Say it again, please.
You introduce another method to find A. I mean, instead of normalization.
No, normalization is normalization. The point is that when you have definite momentum, right, you lose the information of space. I mean, if you plot this, so let's say phi is e to the ikx, okay? If you plot phi squared and it goes from minus infinity to plus infinity, its probability, no matter what A is, its probability is the same everywhere. Okay? That's the dilemma. Okay? We have a mathematical workaround for this.
Like, instead of normalized in the space, normalized in the momentum space.
No, we stop bothering ourselves about particles that have certain momentum and have no bounds. We stop bothering ourselves. Those kinds of particles just does not exist. Every particle should have some standard deviation in its momentum. That's the solution to this problem. I don't know if it diffused to you this information. Let me give you some time. What did anyone understand what I just said? Yes, tell me.
Like, are you effectively saying that free particle does not exist?
Yes, free particle with definite energy does not exist. Free particle with definite energy does not exist.
Without energy or momentum?
Hmm?
With definite energy or momentum?
Well, free particles' momentum determines its energy as well. Free particle with definite momentum and definite energy doesn't exist. There is always an uncertainty in its momentum, and even if it does exist, we just simply don't know where it is. So isn't not knowing where it is equivalent to it doesn't exist?
No.
Very political. It's here, there, everywhere, like, and hence it's nowhere. All right, let me stop walking around to the truth. And the truth is that you always have some standard deviation. I mean, you have to think about some standard deviation in terms of momentum. Okay, so how do we deal with this? To deal with this, we need to remind ourselves about the bounded systems and continuous systems. Okay, so when you have a discrete energy, let's say, you have basically E of n and corresponding phi of n's, right? And you would start with Cn phi n. Do you remember this? We have gone over this multiple times. And your time dependence would simply be this. Okay? Here, n is integer. Now, when you have continuous energies, then you have Ek, which has its phi k, and k is rational number. Okay? The rest is the same. So you actually define x0, not the same. I mean, you define the starting point in terms of these coefficients, ck, phi k, dx, minus infinity to infinity, right? I am confused. Can you give me some time? And hence, I don't have this in my notes, but I hope this is correct, that you can write the way that it behaves like this. okay, you simply turn into integrals instead of summations. All right? So, what do we do about this normalization problem? Well, phi k's like look like this, right? So, for example, for a certain k, it's a wave like this. For a certain k plus delta k, let's say, is it shorter, a bit shorter, or a bit longer? Shorter wavelength. So let me draw it shorter. It's visibly shorter, right? And k minus delta k is longer, a bit longer, right? So this is your phi k minus delta k. This is your phi k plus delta k. And you multiply these by some coefficient, ck multiplied by ck plus minus delta k. You multiply this one by ck plus delta k. Okay? Once you have multiplied it with them, you sum these up, okay, to get your wave function. Okay? And it is possible to get something that looks like a package. Okay? If you use certain coefficients, certain ratios of the coefficients, you can create a wave package instead of a wave that extends to infinity. So it will have, so let me plot these ck's. So I'm going to plot these ck's with respect to k. So let's say this is actually k0, some certain momentum that you have picked up, and okay, you are convinced that you are not getting a certain momentum because that particle doesn't exist. Okay, what's the next best thing is to be at certain k0, but to be around it. Okay, so if you plot these ck's that we have discussed, it looks like this. There is some k0 over here that you want the particle to have, and your coefficients are arranged around it. Okay? You can make it as narrow as you want, but you can't go all the way. That's not allowed. Okay? Do you have any questions at this point? Have I lost you completely? Let's look at a certain code. Maybe this will make a bit sense to you. So, what code is that? Hopefully it is this one. Okay. This is actually tunneling code. Okay, so let's watch. So that's the next subject. There is some free particle with a certain energy. This is showing the energy, and this is showing the barrier. This is the barrier, so it has higher energy than the electron's energy, and it shouldn't be possible classically for the electron to move to the other side. Okay, but as you can see, it actually gets past that barrier and goes to the other side. So there are this multiple weirdness that happens in quantum mechanics. That's the next weird thing that we are going to discuss. But before going there, let's just figure out, so let me put the barrier to 0.
Do we have 2 electrons now after the barrier?
Very good question. No, it's the same electron. It's both on the other side of the barrier and on this side of the barrier. When you do the measurement, it will either appear on the other side or on this side. Okay? But
so the magnitude of that wave are the probability of being there or there.
yes. Very good. So, as you can see, we do have a particle that is moving in one direction, and it's like a package, a wave package. So let's see how we got it. We are getting this wave, initialize the wave function. Instead of giving sines and cosines, I'm giving this range in k. Do you see? So let me switch to the notes. Actually, this is k, and this is ck. Okay? So k in our code, k goes between 10 and minus 10. So 10 and minus 10. Okay? This is k. And what happens? I have a particle centered at x equals to 20. Let's come back to that particle now in a moment. Do you see the energy of the particle is set to 10, okay? And that's where we derive our K0. What is K0? It's basically the, okay, what is K0, for example? 1.62, right? So we have decided to give our particle that much momentum, okay? K equals to 1.67, let's say, okay? What do we want to do? We also have this standard deviation of k. So k divided by 10, k0 divided by 10 is the standard deviation in k. So uncertainty in momentum. What does it mean? It means that we have this kind of ck there, okay? And that's the standard deviation, right? Then we make a Gaussian around K0. Do you see the Gaussian around K0? There's a Gaussian k minus K0 squared over 2 over standard deviation squared. That's how you define a Gaussian, right? Very good. Then I use those CKs, these are CKs, and multiply them with e to the I k x minus x0. That's how I get my wave function centered at x0, okay? That's it. That's how I get my k. So we can play with this k. For example, if you have, let's have much less standard deviation, okay? Then, as you would expect, the problem started when we had certain momentum, right? When you have certain momentum, the wave function is basically everywhere. Are you following? Yes? No? Let me show you. So, all right, sorry. So this is K and this is CK. Let's start with something like this. And this is the wave function. For the green one, I have rather normal envelope, and inside I have the function. Okay? For the red one, let's say, which is more localized in the K space, okay, more localized and sharp, I have more extended wave. So that red one will be more like this. Are you following? And more spread out here, okay, will be more localized here. Does it make sense?
Is it Heisenberg?
Yes, it's Heisenberg. Yes, science. Okay? Exactly. It's Heisenberg's uncertainty principle, and you are witnessing it. So let me decrease the standard deviation. Then I get a localized particle. Well, it was localized before it started spreading out, at least. So let me make it less localized. Do you see it starts localized? Are you watching it closely? Yes? Why it spreads? Very good point. Who is going? Time evolution. Very good. So here's the thing. Why it spreads? Very good point. What did I do to make it localized?
You increase the uncertainty of the momentum.
Exactly. So to get it localized in space, which was this case, to get it localized in space, I used a lot of momenta, right, to construct it, which means that that particle, its wave function consists of a lot of eigenstates that move at very different velocities. So I used a lot of different velocities to construct a certain position. So uncertainty in velocity shows itself in the time evolution, because that particle has a problem with velocity, has uncertainty in velocity, so it has to spread out to account for all those possibilities. Could have been going faster, could have been going slower, could have been going to the left, could have been going to the right. So what happens is that as the time moves, it quickly spreads out. Because of these velocities, these different components of velocities that I had to use to make it localized.
So we are going to sharpen momentum as the time.
I think, unfortunately, not. Do we, though? No. Eigenstates are the same. You are right. So, actually, in momentum space, it stays the same. Okay? But, yeah.
As time going forward, we are losing electron.
So we're losing the information about its position, yes. Yes. Very good.
We cannot calculate the exact momentum over.
When you calculate the exact momentum, then the particle is everywhere. Yeah.
By time evolution, I'm asking that we have a momentum, distribution, and we have a sharp in a position, and after time going forward, it spreads. So we are losing the electron, the
Position.
but we cannot also calculate the exact momentum. Momentum is the same.
Yes. What happens in reality is that you are measuring both position and momentum anyways with a certain precision. Okay? And depending on your precision, for example, let's say if you are measuring it with high precision in space, you are using more high energy lasers, right? So you are disturbing the particle so much that you lose the momentum anyways. That was the thing that, when Heisenberg came up with this, we are done with the lecture. So let's keep talking about this. Sorry, no one is saying that we are done. Let's talk about it later. Also now after the break, with you.